Okay, so as I said, I think it's a good idea to have some discussions on Poisson summation formula because I'm going to use it. So I'll just first give the simplest version in one dimension, and then we will generalize it more and more and see what it really means. So first of all, in 1D, so let's fix a function. So this function, I'm going to kind of vaguely say that it's smooth enough and it has decay enough. Smooth enough plus decay enough at infinity. I mean, you can make this more precise, but that's not the point. I mean, you can take, for example, a Schwartz class function. The arguments you have to give is exactly the same as you do it in one journal. So the point is to understand what then you can do. So if you have such a kind of, let's see, nice function, then the statement is that sum of f of n belonging to z is equal to sum of f hat of n belonging to z. So here f hat is the Fourier transform of this function. So f hat of c is equal to integral minus infinity plus infinity f of x exponential of minus I x c dx. Actually, I'm going to put 2 pi I, so that's pi I x c dx. So this is Fourier transform of f. So Fourier transform is kind of, you have to be worried about it because there are 4 or 5, I don't know. There are many different conventions about Fourier transform, and it can make your life miserable if you switch between different conventions. You get constants wrong, you get signs wrong, you get everything wrong. So it's very important to fix some convention and get used to that, and to be aware that there are other conventions. So you may see formulas in a different form in other sources. So you should always check that the conventions for Fourier transform is the same as. So this is our Fourier transform in this case, just to make sure that's what I'm using. Yes, that's my convention also. Anyhow, so this is the formula. So, I mean, if you look at it, it's an amazing formula, right? I mean, y summation of values of f, so this is like f, right? So this is f, and you can look at, so, and then f hat looks quite different than f. Except that if f is very spread, f hat is narrowed, and there are things like that. But in general, the relation between the two is quite complicated. So I mean, I can just say maybe here and something like that. So this might be f hat. I'm not sure even this is correct. So this formula is quite remarkable, right? Now, to prove it, first of all, I'm not going to prove this, but I give you hints to prove it. So the first proof. So given this f, you can create a periodic function by averaging over the action of this group Z. So you find g of x to be equal to sum of f of x plus n and belonging to Z. So you're averaging. And this decay at infinity will guarantee you that this sum is again convergent and is nice enough function. So in particular, this g is periodic. Z periodic. And so you can take its Fourier series. Now we are talking about Fourier series, right? So to get g hat of n, these are the Fourier coefficients of g. So in general, of course, Fourier coefficients, you know, again, this g hat of n is equal to integral from 0 to 1 exponential of, well, let me put it like this, g of x exponential of minus 2 pi I n x dx. Right? So it's a number that you create out of this function, g. I mean, this is in general for any g, you have that. And then what you use, again, is a general fact, which is Fourier inversion formula or Plancherel's formula. So this is, we could call it Fourier inversion formula. Fourier Plancherel inversion formula. So what does it say? It just says that you can write your periodic function g in terms of this Fourier coefficients and the fundamental characters, right? So g of x, you can write it as sum g hat n, right? And then exponential of 2 pi I n x. Yes. Exponential of 2 pi I n x, n belonging to z. So you can recover g from this g hat by this formula. Now, in particular, if you put, for example, x equal to 0, then you get that g of 0 is sum. On the right hand side, you're going to get g hat of n, right? N belonging to z. So if you go back to your original definition, g of 0 is the values of f, sums of values of f on the lattice points, right? So we get that indeed from here you get that sum of f of n belonging to z is equal to sums of g hat of n of n belonging to z. And then this sum, we can compute the Fourier coefficients of g using Fourier transform of f. Because the Fourier transform, which is defined like this, you can chop it into different pieces, sum over different intervals, and then you use translation invariant of Lebesgue measure to reduce everything in terms of this g hat n's, and then this turns out that this is indeed equal to sum f hat n and belonging to z. So this is your first proof. But notice that actually this relation here tells you that you can prove more. I mean, you can just say that sums of f of x plus n's, without putting x equal to 0, you can compute at x plus n's and add, and then it's equal to this sum. And this g hat of n, again, is your Fourier coefficient, so you get sums of two things. The values of Fourier transform at n times the character at this point. So this is a more general version of Poisson summation formula, but this is, for now, is good enough for us, but this can be done. So that's first proof. Okay, that's our first proof. The second proof, it's using, I would say, similar idea, but its emphasis and its kind of tone is different and is much deeper approach. So let me tell you about the second proof. Okay. So the second proof, so this is, so we can define an operator. We can define an operator like LF, I mean F as such. We can define an LF from L2 of R1 Z to itself. So you should think of this as the Hilbert space of square integral functions on the circle. So we define an operator like that. So this operator is basically the convolution product of f and the g over there. So the operator is acting like this. LF of g is equal to f convolved with g. Now you have to worry about something, because this g is defined on the quotient, but that's okay. You compose it with the map. You get a periodic function on R. You compose it with this map, this projection map. So now you can think of g as a function on this big space R, group R. And then this is the convolution. So what is convolution? So f star g of x, you can say this is integral f of x minus y, g of y, dy over R. which is also the same as integral over r f of y g of minus y plus x dy again over r. So this is this convolution. You can easily check that, for example, here, you can check that, first of all, this guy is in L2 by things that we assume. And you can also check that this function, again, is periodic. I mean, this G is periodic. So here we are like averaging or summing with some coefficients of these periodic functions. So it is, again, periodic. So this is a periodic function, so you get a map from this to itself. So this is an operator. So LF is a bounded linear operator. So you can, in fact, now diagonalize LF. So that's a nice thing about these characters is that this LF can be diagonalized. In the basis consisting of characters. So this characters is e to the 2 pi I and x's. The basis, I mean, so orthonormal basis of L2 of R1 Z. Yeah, these are this is an orthonormal basis. I mean, yeah. Right, so because the mass of 0, 1 is 1 in this case, so that's fine. And is so the eigenvalues also you can compute. And but what it turns out is that this actually turns out to be a trace class operator. Trace class. So then what we do, we can compute the trace of this operator in two ways. And compute. So, so this trace of LF, on the one hand, because it's a matrix, on the one hand, we know that this trace is going to be sums of eigenvalues of this matrix. I mean, so sums of lambda I from 1 to infinity. But on the other hand, like the case of matrices, we can also say that the trace is also equal to sums of elements on the diagonal if you write it in any basis. This is sum AII, right? So this formula by itself is like a magic formula, right? I mean, even for matrices, this is quite remarkable. Because you have learned linear algebra in undergraduate, you may not think much of this formula, but I encourage you to think highly of this formula. This formula that if you add, if you give any matrix, if you add elements on the diagonal, and if you add elements, if you add the eigenvalues, you get the same number. this is quite remarkable because I mean, if you think about it, these lambda i's cannot even be computed effectively by algebraic methods because the equations can be of degree 256, right? So these numbers are not accessible to us in some sort of algebraic fashion, although they are solutions of polynomial equations, but nevertheless, their sum is accessible. And all elementary symmetric functions of these functions, lambda i's rather, is also accessible. This is quite remarkable. And we are using analog of that fact in this case. So what it has to do with Poisson summation? Well, it turns out that one of these sums is one side. Sums of eigenvalues is the other side. And this will give you another proof of this theorem. Now, I want you to think about sums of eigenvalues corresponds to sums of f of n's, the value of f at n, with this definition, or is it sums of aii that corresponds to this, and then you have to go the other one. So I won't do it here. I will ask you to do it yourself. So this is the second proof. So I basically gave both proofs. And the reason I'm giving both proofs is that the second proof is kind of very deep and it can be generalized to more or less all groups in some sense. And we'll discuss it. Okay, so two proofs. This proof is sums of eigenvalues is sums of AIs. The first proof is Fourier inversion formula. Essentially, they are equivalent, but they have different tastes. And this is, I prefer this one. Although, I mean, that might seem simpler. And this might be a bit of overkill, but the reason I give again is that this is something that can be generalized, but this is not easily, this method of proof, it's not so easily generalizable, although. Okay, so this was, though, for in one dimension. But what I need, I need it in higher dimensions, and not just for Z, I need it for arbitrary lattices. So let me then go to higher dimensions. Are there any questions? No. Okay, so let's go to higher dimensions then. All right. Okay, so now let's fix a lattice.
Sorry, Masood.
Yes.
Quick question. So in the second proof, where did you use the decay conditions?
Oh, because it comes into the game to show that this is a trace class operator. Those eigenvalues have to definitely go to 0 and also have to be summable. So that's
okay. Thanks.
Yes, and even before that, of course, to talk about even Fourier transform of a function, you need some L1 condition at least. So that's needed, but you need more than L1. You need more than L1. You need, definitely. So now let lambda subset of Rn be a lattice. As we already discussed several times, so this is an Euclidean lattice. Again, let f from Rn to C as before. Smooth enough plus decaying enough. we can show that the sums of values of f over this lattice, so I'm going to put gamma. Sorry. So gamma belonging to gamma, this lattice sum is equal to 1 over, now this is important, volume of gamma, sum hat of maybe gamma star, or gamma star belongs to gamma star. Okay, again, we have to fix our conventions for Fourier transform for functions from on Rn. So f hat of c again is equal to integral over Rn. It's like before. So f of x exponential of minus 2 pi I inner product of x and c. This is the real inner product on Rn. Again, but you multiply by 2 pi I, and there's no coefficients here as last case. And then there is dx. So this is the Fourier transform of this function as we get here like that. So this comes into the right into the right hand side. Now, what is this gamma star? So we also have seen this before. This gamma star is dual lattice. Dual, I mean, physicists call it reciprocal lattice. Lattice. Sometimes also this orthogonal is also used, this notation in physics literature, condensed matter, I mean, solid state, stuff like that is used. So what is that? Well, as we saw before, this is the set of all y belonging to Rn, such that inner product of y with x belongs to z. The inner product. So I'm using this inner product notation. Maybe I just, yeah, no, that's okay. That's okay. The inner product of y x belongs to z for all x belonging to gamma. So it's not a difficult exercise to show that actually this gamma star is a lattice. And that's what we are using to write down the right-hand side, except for 1 over volume of gamma. Now, what is volume of a lattice? The volume of this lattice, in general, is the volume of any system of any kind of basis for the lattice. So let me put it like this: is absolute value of volume of E1, E2, En, where this E1, E2, En has the property that is a basis for your lattice gamma. So you can write gamma as ZE1 plus ZE2 plus ZEN. If that's the definition of a basis, or you can say this is also the definition of your lattice. So we're saying a lattice is a subset of Rn such that there exists a basis of Rn such that you can write gamma as such. In particular, it follows that this gamma is a free abelian group, as a group is a free abelian group of rank n. And also, but more than that, is also discrete, a subset of Rn, and is a subgroup and so on. Now, one thing you should ask is why this does not depend on the choice of E1, E2, En. because indeed there are many different bases for your lattice. For example, in R2, for this Z2 lattice, the standard basis E1 equal to 1, 0, E2 equal to 0, 1 is a basis, but you can take another basis, which is E1 prime equal to E1, but E2 prime equal to E1 plus E2. So if you look at it, I'm saying this and that is a basis, but then this and this also form a basis. You can have, but then you can play this game, you can construct very strange kind of vectors here, which still form a basis. You can have. But the volume is independent of that. In fact, volume is an invariant of the lattice. It's beyond its rank is the first invariant that's accessible and is understandable. Is the Euclidean invariant of your lattice. If you can move your lattice by an orthogonal transformation of Rn to another lattice, this volume won't change. I mean, that's what more or less is saying. So why is that so? Why this is independent of choice of E1, E2, En? And any answers to that by any chance? So the reason is this. Imagine you have another basis, E1 prime, E2 prime, En prime, for your lattice. This is still a basis for Rn too, because, you know. So basically what happens is that then there exists a matrix that takes this basis to the other basis, right? So you can write EI prime equal to AEI. There exists A belonging to GL and R such that EI prime is equal for all I. But now this matrix, because these integral coefficients have to go to integral coefficients, I mean, it follows that actually this matrix must have determinant 1. I mean, so that's not difficult to see, but now somehow it escapes me now. But I don't want to spend time on giving a proof why determinant of this guy is 1. It's basically because yeah, I mean, right. Oh, okay. First of all, this guy belongs to GL and Z, indeed. Look, I mean, you have a basis, you have another basis. This one, you can write it in terms of integral coefficients, coefficients of the other, right? So those numbers that appear in columns are going to be integer. So those numbers are going to be integers. But so this matrix is in GL and Z. But any matrix in GL and Z has to be absolute value determinant 1 because if A inverse, you know, is equal to 1, this and being, so this implies that absolute value of determinant of A is equal to 1. There's simply no way for integral matrices, I mean, also inverse belongs to GL and Z, there's no way for integral matrices to have a determinant plus anything plus minus 1. So this shows that basically volume is independent. In any case, this is the formula in this case. Any questions?
Sorry, maybe I'm missing something really obvious here, but what is the volume of a basis? Are you taking like a matrix of the basis and taking determinant? Or?
I said it's independent, but what is the volume? Right, so the volume is the volume of this parallel piped formed with these E1, E2, ENs.
Okay, so you make a matrix with those as the column and then take the determinant, if I'm understanding?
Yes.
Okay, got it.
Exactly, and take absolute value, right. No, that's a good point. I was thinking about the proof of independence of something that I did not even define for you. Yeah, so, right. So basically, so once you pick a basis, you form this parallel pipe, right? E1, E2, and you compute the volume of this guy, which is absolute value of determinant of this matrix or whatever. Well, I mean, it's a compact subset of Rn, so has a volume, so you can take its volume. Right, so you can take its volume. So, yeah. Any other questions? Okay. So now in this case, we have this nice formula. We have this nice formula in this case. And the point is that exactly the same proof works here. No more, no less. So both proofs actually carry over to this case. So both proofs. Work in work here as well. And you might wonder why this volume term appears. Well, the volume in the case of Z lattice is equal to 1 because you can take this as your basis. In fact, this lattice, Z lattice doesn't have any other but two bases. This one or minus 1. There's no other basis for this lattice. And if you compute the volume of this parallel pipe here, you get 1. So that's good. Of course, if you have some lattice like AZ, then its volume is going to be absolute value of A, right? It's this one. And the reason that 1 over volume comes because when we take those characters and Fourier coefficients to normalize, to get into the hard measure, you have to divide by some factor, which is the volume of this fundamental domain. So by the way, I mean, this is called fundamental domain. So a fundamental domain once you fix a basis for your lattice, then it's a set of the four sum AIs. AIs less than 1, bigger than equal to 2. So you can just say a volume of your lattice is equal to volume of any fundamental domain. There are many, many fundamental domains, right? And this is the so that's the proof in this case. Okay. Now, why? So this Poisson summation formula is it's very, very important. I mean, for many things. I mean, for number theory, for applied mathematics, for pure math, for in analysis.
Could you comment on why the dual lattice is playing a role?
Sorry?
Could you comment on why the dual lattice is playing a role?
Or dual lattice plays the role because of characters. You want to take the characters of your lattice. I mean, so yeah, it's because of Fourier duality. Essentially, that's why they enter into the game. So so let me just say right, something like this. So if you look at Rn over gamma, so this is a torus, right? So this is a compact abelian group. Compact topological abelian group. It's a torus, right? Topologically, it's a torus, and it's a torus.
Yeah.
Okay. Now, we are interested in looking at characters on this dual torus. Characters on the dual torus. So characters on well, this is a compact abelian group. The space of characters is a discrete space, which is a one-dimensional unitary representations of. So let me tell you what is this. This guy is a set of all maps from here to U1. One-dimensional unitary representations of this group, which is the character group, and it's also called the unitary dual in this case. So what happens is that these characters are exactly, they can be identified with elements of the dual lattice. Okay, so there is a one-to-one correspondence between this and infinite gamma star. So let me tell you why. Do you see that why there is this one-one correspondence?
Well, I just need to tell you where each of the bases goes to inside U1.
Basically, these are these elements of the dual of Rn that go to 1 on gamma. But the dual of Rn, we know they are elements of the form e to the 2 pi I xc. But because they have to go to 1 on gamma, it means that they have to take integer values on gamma. Taking integer values on gamma means that x dot c has to be in z. For elements, x dot y may be y in gamma, and this is exactly elements of gamma star. So that's the way this dual lattice appear in this game. Yeah.
Okay, thanks.
Yeah, sure. No, this was a good point. Okay, so so we have that, and then any other questions? Okay, so now let me tell you why. So as I said, this is a very general fact, and I will comment on this equality because this equality has something extremely beautiful in it too. But right now we don't see it quite. We cannot see it quite like that unless I introduce some concept which is so I keep it, but then I'll just say, okay. So now let's introduce Gaussians. So this Gaussian is this function exponential of minus pi x squared in one dimension, or exponential of minus pi norm of x squared. In general. So let's take your function f to be this. Because this function has is infinitely smooth, in fact is analytic, and has of course rapid decay. It's a Shor's class function, I think. Now the beautiful thing about this function is, I mean, this sort of normalization is amazing, because first of all, always this is equal to 1 in all dimensions. There is one formula that always works in all dimensions, and that's this one. It is incredible. And second of all, its Fourier transform is exactly equal to the function itself. Is equal to exponential of minus pi norm of x squared, equal to f of x. So that's a function that's kind of self-dual with respect to Fourier transform. I mean, that's really very nice. Of course, follows that the Fourier transform of any multiple of this one is essentially Fourier transform of this by 1 over that coefficient. But but this is what you want to remember about Gaussians for now are these two formulas. It's a distribution. It's normal distribution, and standard normal. Well, it's not a standard normal. It's this one. It's normal, but its mean is 0. What variance is not. I don't know what the variance is in this case. But anyhow, this is the second property. So we are going to apply this now to lattices. So apply Gaussians. I mean, feed into the lattice. Sorry, feed into this trace formula. I mean, this Poisson summation formula. These Gaussians, or apply Gaussians to Poisson summation. Okay, the lattice I'm going to get, so fix a lattice, and then I'm going to apply this to family of lattices, like this. So the lattices you want to take are gamma t is equal to root t times gamma. Okay, so take any lattice you want, and then form this new lattice, gamma t equal to root t times gamma, t positive. Right? And then Poisson summation formula tells us that. This formula tells us that sum exponential of minus pi t, a norm of gamma squared, gamma belonging to gamma, is equal to t to the power minus n over 2. Yeah, I think I can still write here. Minus n over 2 sum. Okay, so times 1 over volume of gamma times sum exponential of minus pi norm of gamma star squared, gamma belonging to gamma star, right? it's a simple application of this result to this family of lattices. Of course, there is a relation between volume of root T gamma and volume of gamma. The factor of T to the power n over 2 comes out. And that's the factor here, 1 over volume gamma stays. And this is the right-hand side, this is the left-hand side, and that's, oh, there is a T here. I have to divide, I forgot. So this, it's divided here, it's multiplied. That is always, anyway. So this is the formula that follows from Poisson summation formula. If you apply it to Gaussian and using the fact that with that normalization, the Fourier transform of Gaussian is the Gaussian itself, this normalization, in any dimensions. So now, I can introduce some notation, namely theta series. This is also called theta function. Of a lattice. So this is theta gamma of t is equal to sum exponential of minus pi norm of gamma squared, gamma belonging to gamma. Right? That's this theta function for the lattice. Obviously, it's a positive valued function, which is absolutely convergent, very nice for t positive. And I think I can erase this. And it also, you know, it, do you know what's the limit of this function as t goes to infinity? Oh, there is a pi. No, I need a t factor. There should be pi t. Yes, pi t. Sorry. Yes. You know what's the limit of this function as t goes to infinity?
Suspect 1?
It's 1, yes. It's 1. Because if you study this, you can write it as 1 plus terms. Well, I mean, if gamma is equal to 0, no matter what t is, you're going to get 1. So this 1 stays no matter what t is. But then there are terms that are rapid decay. But this gamma belongs to gamma, but gamma is different from 0. So if you analyze these things get bigger and bigger. As t goes to infinity, they become smaller and smaller, and they are always, the dominant term is the first one, the point that's closest to the origin, or points that are closest to the origin. They give the dominant term, the rest, and though that dominant term also goes to 0, so this goes to 0, this goes to 0. Okay. So that's 1. And what happens to the function as t goes to 0?
It blows up.
It blows up. It blows up badly, goes to like 1 plus 1 plus 1 plus 1. So, and in fact, the function is decreasing, nice function. It's just like that. It goes to infinity, definitely. And keep that function in mind. There exists a kind of one-dimensional case for gamma equal to z, which is the theta series. We discussed it last time, exponential of minus pi n squared t, n belongs to z, right? This is the series that we discussed last time. This is the standard classical original theta series that was kind of brought into the main character, brought in as a main character by Riemann, but this was the third theta function, or its complex analog, introduced by Jacobi. So Jacobi had like 4 of them, but Riemann decided that these types are most fundamental for Riemann surface theory, and he brought them into the as the main characters. These are, we can say these are Riemann theta functions essentially, but they were introduced by Jacobi. Anyhow, so that's this one. So what this formula tells us about the relation between theta function of a lattice and the theta function of the dual lattice now. So this relation now is telling us that, it's telling the following: theta gamma t is equal to, well, there is this t to the power minus n over 2, 1 over volume gamma, times theta of what? Some expression here I don't want to spend any time on that. Theta gamma of 1 over, yeah, theta, yeah, theta gamma star, yes, of 1 over t. Yeah, this is the formula, right? Do you see that? It's pretty straightforward from this formula, right? If you just write down using this definition, we are going to get this formula. So, okay, so now we have the relation between theta function of a lattice and theta function of the dual lattice, but at different temperatures, so to speak, or at different times. This is at t, this is at 1 over t, and there is this factor over there. Okay. Now, what do we want to do with this? Right, now assume that you, first of all, let me make a little bit of comment about this theta function. You see, 2 lattices, now this should be clear. 2 lattices are, how to say this? If the theta functions of 2 lattices are the same, then you can go on and show that all these lattice points are the same. So, in other words, there is exact amount of information in the lattice as it is in its theta function, because, so let me make this a statement. Theta gamma t is equal to theta gamma prime t. If and only if I mean, okay, so if and only if they have the same lengths, this set of norm of gammas, gamma belonging to gamma, with multiplicities. So this is a kind of multiset with multiplicities. It should be the same as gamma primes, gamma prime belonging to gamma prime. I mean, one way, one direction, of course, is obvious, right? But the other direction is not bad either. If you put this equal to minus pi t norm gamma prime of t, equality for all t prime, you can start from lower, from the biggest terms. Those leading terms have to match. First of all, bonds you can cancel, and then the leading terms have to match, and the number of those leading terms also have to be the same. Otherwise, you're not going to fix this equality by tampering with lower order terms for all t, because lower order terms for different t's they're going to decrease, and you're going to spoil the equality. That's what I'm saying. So, but notice we are not saying that the lattices are the same. We are saying that the lengths of members of the lattices are the same. And lattices can be different, can look different. For example, they can be isometric to each other. Then the length structures, length of vectors in the lattices are the same. You can rotate this lattice, but then you get the same theta function. So basically what happens is that this theta function is an isometry invariant of the lattice. In other words, two lattices are isometric if and only if their theta functions are the same. So this is a complete isometry invariant of lattices. So let me write it here, although I don't think I'm going to use it, but let me write it here, this theta function. So lattice theta function is a complete in the sense that I mentioned, complete isometry invariant of the lattice. Yeah, so I don't want to get into more detail about this right now because I don't think I use it, but this is something to keep in mind. Okay, now what we can do with this is the following. Assume you have a lattice that's self-dual, okay? Assume gamma is equal to gamma star, so self-dual lattices. Okay, then and unimodular. Unimodular means that volume of gamma is equal to 1. Now, would self-dual, I think self-dual implies that it is unimodular, right? I think the formula is this: volume of gamma star is equal to 1 over volume of gamma. This we know. So if gamma star is equal to gamma, then you can conclude that, well, because it's a positive number, then volume of gamma is equal to 1, so it's unimodular. So I can say, then this implies that, so unimodularity follows, volume of gamma is equal to 1. If you have a lattice that's self-dual, then volume is 1 also, and then we get this beautiful equation, which is theta gamma t is equal to t to the power minus n over 2 theta gamma 1 over t. So this is a famous equation. This is called Jacobi inversion formula for theta series, theta functions. So this is Jacobi. Jacobi had this relation exactly, but this was not his proof. I don't know how he proved it actually. It kind of baffles me how he could prove this without any analysis basically. So this is called Jacobi inversion formula. For theta. This is also called functional equation for theta. Functional equation for theta. It's also called functional equation for theta. Okay, so the case that first came across, Jacobi did that case first, was n equal to 1, and then this was the formula that theta, z t, by definition, let it be equal to theta t. Then Jacobi indeed wrote it theta t is equal to 1 over root t, theta of 1 over t. This is for all t positive. Now, if you think about it, it's okay. Imagine this is given to you as an exercise or problem in calculus, because you can give this problem to your undergraduate student, to first-year student. Both sides make sense, right? Both sides make sense. So let us write it. I mean, what this says, it says that sum exponential minus pi n squared t, n belonging to z, is equal to 1 over root t, sum exponential of minus pi n squared, pi n squared over t. Yeah. So if you think about it, I mean, this is not obvious. I mean, if you can give me a proof of this without all these steps that I've taken, I will give you $10. And maybe you can even write a paper using the new method that he invented. So I believe Jacobi did not have that technology at all. He just proved it somehow. I don't know how he proved it. By algebraic manipulations, by what? I don't know. I mean, this is anyhow. So this is called the functional equation for theta series in this simplest case, and or Jacobi inversion, because so it kind of relates these two things. Now let's go back to now let's go back to spectral decompositions, and this is stuff that we did, and let's see what each side of the equation is telling us, and what each side is measuring for us, basically. Okay, right. So very good. So let's go back. So I mean, so there is a famous counterexample in spectral geometry, which I don't want to talk about it here. but this is due to Milnor based on work of and Smith. He gives two 16-dimensional lattices, which are isospectral, but not isometric. So the theta functions are the same. So they are isospectral, they're isometric to each other. No, they're isospectral. Okay, let me not get into that because I'm going to confuse myself and yourself even more. So let me not get into that. Let's go back to, first of all, any questions? Okay, so now let's see what this side means. So back to Laplacian. Okay, so now let's look at Laplacian delta, which is minus some pi squared going from C infinity of Rn mod gamma, right? This is the torus to itself. So this is the flat. So this is Laplacian for flat torus. It's Laplacian for flat torus. I mean, so what we do here, of course, we have Rn to Rn over gamma. We have flat Euclidean metric here. This is a covering space. You can push it down. You get a metric, Riemannian metric here, which is still flat. And this is Laplacian for that. It's going to that. So this Laplacian, we found its eigenfunctions and eigenvalues, right? Delta phi equal to lambda phi equation. Here, it has solutions that we know what they are, right? Do you remember the solutions? We said that phi gamma star of x is equal to e to the 2 pi I inner product of x gamma star. So this is for any kind of gamma star belonging to the dual lattice, right? These are, so in other words, what it says is that the dual lattice parameterizes points of the spectrum, because lambda, so delta of phi gamma star, in fact turns out to be equal to 4 pi squared norm of gamma star squared, right? Phi gamma star. So lengths of this vectors in the dual lattice, rather squares of lengths, it's exactly the spectrum of this Laplacian. So let me write it. So spectrum of this Laplacian. By results that we proved, we know that this Laplacian has only discrete set of pure point spectrum, basically. And it's a discrete set. It goes to infinity, da, da, da. And in fact, we know this is exactly the set of points of this 4 pi squared norm of gamma star squared. The gamma star belong to gamma star, the dual lattice. And you notice why we want to be in the dual lattice, because if you pair this with a point on the lattice, you're going to get 1, so you're going to produce a periodic function as a result of that, right? So that's okay. So this theta function for one side actually encodes a spectrum of the Laplacian. So spectrum of the Laplacian is encoded by one side of this Jacobi formula. Now let's see what is the other side that's encoding, right? What's the other side that's included. So I'm now asking the question, what is the importance of the lattice points, lattice lengths itself? So the other side. I mean, you have to put a bit multiplicity here, right? I mean, because you can have different points in the lattice that have same distance to the origin. For example, a square lattice is just like that, right? Points that are on the vertices of the square, right? I mean, they have distance to, same distance to 1 and so on. But that's fine. So you get multiplicities that way. For each eigenvalue, you have many of them that have same length. So that gives you the multiplicity. Okay. Should I explain this more or you understand? I think that's okay. Now, what is the importance of these guys? So this is also very important, but its importance is not in terms of differential operators or quantum mechanical information. Its importance is in terms of geodesics. So these guys are related. Actually, they are exactly lengths of geodesics. So let me introduce the length spectrum. Length. So this is Laplace spectrum, right? Laplace spectrum. We have the Laplace spectrum, which is that. Now let's look at length spectrum. So length spectrum is this. By definition, is the set of all lengths of gammas, where gamma is a closed geodesic and in this way of writing these numbers, we are just looking at geodesics up to free homotopy equivalence, okay? So, I mean, so up to, so here we are considering geodesics up to free homotopy so what's going on in this case? So let us look a bit more carefully. So this is this is a definition. It's a precise definition, I guess. Now what we want to do is to understand. So the claim is that this is actually equal to lengths of gammas. I mean, gamma. Oh, so no. Okay, so this is a very bad notation. So let me put it like C. I'm sorry. This is C is a closed geodesic curve on the torus, where we are looking at geodesics up to free homotopy equivalence. And now I'm claiming that this is, so okay, so this is a definition. I'm claiming this is equal to the set of all that's exactly a length spectrum of gamma. I mean, that's really exactly equal to the set of all lengths of vectors in gamma. Yeah, that's the thing. Okay. So this is not obvious at all, right? Because I mean, these are lengths of closed geodesics, and then geodesics that can be moved into another one by free homotopy move of this curve inside the torus to another one. For example, all those that form the belt, kind of one belt along one kind of direction on the circle, we can all rotate 360 degrees. All of them constitute only one geodesic, which is the geodesic that comes from. And also, multiples of those also should be counted, twice, 3 times, and so on. So why that's the case? Well, I mean, the point, so let's look at the case gamma equal to, for example, Z2, right? Oh, okay, I mean, let's look at a case of gamma equal to Z. Gamma equal to Z. What are the geodesic, closed geodesics of the circle up to homotopy? I mean, these are just R mod Z, R mod gamma is S1. In this case, of course, geodesics are this go around once, length 1, because I'm taking circle of length 1, right? And so this is, in this case, that's completely obvious. Okay. Now let's look at the case of n equal, so this is n equal to 1. Let's look at the case of n equal to 2. So we have got R2 to R2 over Z2. So this is your lattice, square lattice. And we have got, so we have got this map here into torus. Right. So now imagine you have a closed geodesic here, and of course a flat torus, right? So imagine you have a closed geodesic here. Okay, it's closed, it's geodesic, and so on. Okay, what can we do? What we can do is that we can lift this geodesic to R2, right? So this is the projection map, right? So you can lift your geodesic to R2. So you pick an initial point, any point you want, that's okay. There could be many points. I mean, they are defined only up to action of Z2, right? So you pick any point, and then when you lift it, because this is a flat torus, this is going to be lifted into a straight line, right? It's going to be lifted into a straight line. Okay. And because it's closed, the difference between this and that point is going to be, so this is B, A, this is B. A minus B is going to be in point in Z2. Right? A minus B is a point in Z2. And because we are considering everything up to free homotopy, you can just move this here, and then you're going to get, and so you notice that then as a result, the length spectrum of this manifold is no more, no less, but lengths of lattice vectors. So lengths of closed geodesics up to this free homotopy equivalence and so on is exactly this number. So now, what this formula tells us, the formula that we have, Now we have seen now. So now the formula shows the following amazing thing. If two lattices have the same length spectrum, they have the same Laplace spectrum. And if they have the same Laplace spectrum, they have the same length spectrum. So they determine each other. So let me write it. That's the kind of message to drive home now. That's the deepest message today. So let me write it. So now the formula. So let me call it the trace formula. You remember the formula in terms of, we have this formula which is sum exponential of minus pi t norm of gamma squared, right? Gamma belonging to gamma is equal to t to the power of minus m over 2, 1 over volume of gamma times sum exponential of minus pi norm of gamma star squared over t gamma star belonging to gamma star. So this is what I call a trace formula. Now I don't think I used this term before, but I'm going to call this a trace formula. So this trace formula, which is this one, implies that the length spectrum determines the, so right hand side is the Laplace spectrum, right? Is the theta function associated to the Laplace spectrum, essentially. Well, there's 1 over t, but that doesn't matter. It shows that length spectrum and Laplace spectrum are completely determine each other. So, I mean, I'm writing it like this, and Laplace spectrum. Determine each other. So this has a deep kind of interpretation in physics that gives a relation between quantum mechanics and classical mechanics. You see, in classical mechanics, if we don't have any potential on this flat torus, particles will move on geodesics. That's what we know. In classical mechanics, particles move on geodesics, right? So this you can write it as classical mechanics kind of correspondence to. So I'm kind of right now rather vaguely I put it like this: determines quantum mechanics and so on. You see, in the quantum case for Hamiltonian, H is equal to T2 over 2n, right? Plus 0 because there's no potential. So this is 0. And this turns out to be just Laplacian. That's minus Laplacian. Well, it's actually, in my notation, well, the physicists always put minus delta, but geometers always put delta because geometers, the Laplacian is positive. That's the Hamiltonian. So a spectrum of the Hamiltonian is exactly a Laplace spectrum, but the periods of motion, classical motion, is a length spectrum, and well, yeah, I mean it's a period, right? So I mean then they determine each other through this formula. So this formula is really a remarkable formula. So now, of course, now the question is, can this be generalized? Can we generalize this? So you have a compact Riemannian manifold, doesn't have to be flat or anything, just closed. You have the Laplacian, and we have the spectrum of the Laplacian. So we have this Laplace spectrum on the manifold. And on the other hand, we have also length spectrum. So we can take lengths of these closed geodesics up to homotopic, free homotopic equivalence of geodesics, and look at those. Is there a relation between the two? Is there a formula or kind of a statement that would say one can derive any information from the other one? So that's a general question, right? So let me write somewhere. Any question about this? Right. So now let's let me write it now. Okay, so let me write it like this as a question.
Is this not the famous can we hear the shape of a drum question?
What is it?
Is this not the famous can we hear the shape of the drum question?
No, it's not.
Okay.
It's not. The shape of the drum question is related to Laplace spectrum, but that's much easier to formulate. It basically says that is it true that two isospectral manifolds are isometric? Because isometry means shape, drum means a spectrum, and that's it. So that question was asked even before it was asked, I think amazingly maybe a year before, 2 years or something like that, very closely. Well, this question must have been in the air, and people perhaps privately or in some circuits have been asking this. But when Mark Katz wrote that famous article, I think in '66, already, I guess, I'm not sure, maybe Luke have seen this, in '65, Milnor already had given examples of two, well, okay, so no, okay, so Milnor, Katz knew about Milnor's result. I'm not sure if he cites Milnor or not, but Milnor gave examples of two flat 16-dimensional tori that are isospectral but are not isometric. So this I will do at the beginning of my spectral geometry course next time. I mean, you have to develop these ideas, and then from here, you have to introduce this sort of Lich lattices, and so those lattices were actually found by Ernst Witt in 1940s, German number theorist. So that's so that's 16-dimensional. Then there was a long quest to bring down the dimension and get simpler and simpler manifolds, and eventually two polygonal domains in R2 were constructed that are isospectral but not isometric. But the question for a smooth bounded domains with the smooth boundary, I mean, domains in R2 is still open. So if you make an advance on that, you will be you're going to hit gold for sure. You're going to land a job in a very good place immediately if you do that. So that's a very good question. There are a lot of things. So that's the question about can you hear? Well, it's not can you hear. It's can one hear the shape of a drum? It's can one hear the shape of a drum? But this is different. This is a relation between quantum mechanics and classical mechanics, and it's in the guise of trace formulas. So how to generalize this? To other manifolds. So there is a case, there's a very well-known, famous case that was done by Selberg. So this was in 1950s. So what we did, we looked at flat tori, right? Selberg looked at hyperbolic surfaces. Riemann surfaces. Of genus bigger than or equal to 2. And these Riemann surfaces, by uniformization theorem, we know that there exists a metric on this which has constant curvature -1. Uniformization theorem tells you that there always exists such a Riemannian metric. And you pick that, you get that. So then you are in business to ask the question. And Selberg, there is a formula, much more complicated than this, that shows that the Laplace spectrum determines the length spectrum, and length spectrum determines the Laplace spectrum. So that's the case of Selberg. I think after Selberg, it was generalized to other symmetric spaces. And then it has been going on, has been generalized to many cases. So that's one direction of these trace formulas. But there is another direction which you don't get exact equality, but there is something in that case, which is, I think there is some work, I have to mention Colin de Verdier. I hope my spelling is right, I'm not sure. And then there is also work of Gilliman. And I believe there is Duistermaat also. I think Gilman and Duistermaat work together. So they have some analogs. It's not exactly like this. Some analog of this for generic closed Riemannian manifolds. I think so. I have to. I think get the exact formulation. So these sort of ideas are kind of running deep, quite deep in mathematics. And also there are analogs of these formulas in number theory. In that case, they're also called explicit formulas or trace formulas of number theory. So, for example, Riemann has one of them. So that's okay. Any other questions? Or now, because I mentioned Riemann, let me tell you, Riemann, we use this relation to prove something immediately. And then I'll go back to I'll go even further back to what I was doing in the last lecture. Because there was this issue of getting asymptotics near zero. Okay, so a first dramatic application. Relation theta of t equal to 1 over root t. So this was done by Riemann. That was in 1859 in his famous number theory paper. So he gives a proof that he shows that the star implies functional equation for Riemann zeta function. So remember the Riemann zeta function, zeta s is equal to sum 1 over nps, and from 1 to infinity. This is originally defined for real part of s bigger than 1. On the right hand side of here is defined. I mean, it's a holomorphic function. It's a nice holomorphic function defined everywhere on the right-hand side, strictly right-hand side. Then Riemann, in his second proof of this functional equation, he showed that you can use this. I can do it. Give me 1 hour. He showed that this, first of all, implies that the function has analytic continuation everywhere except that one. One, there's a pole at one, because as s goes to 1, this blows up. There's no cure for that. There's only a single pole at 1, everywhere else holomorphic, and also satisfies the following equation: z of s is equal to z1 minus s, where z of s, this is called the completed zeta function. So this is equal to gamma pi to the power minus s over 2, gamma of s over 2, zeta of s. So you complete it. You multiply by gamma function at s over 2 and pi to the power minus s over 2. Now, why you have to multiply by this? If I give you the proof, you understand these objects appear more or less naturally if you know what gamma function is. So then what Riemann did is that this relation actually, in fact, is equivalent to this relation, or what did, yeah, this relation. So that formula implies that this function around s equal to, so zs around s equal to 1/2 is symmetric. Its values here and here are completely determined. I mean, yeah, by each other. So on. Well, I mean, this equation is very, very important for this famous functional equation. It's very important for Riemann zeta because basically tells you that the values on the left-hand side is determined by values on the right-hand side of the critical line, and all zeros, except for trivial zeros, which are going to be at negative even integers, are going to be, okay, so that's the conjecture going to be on the critical. But this was, so this formula is a big deal because it's equivalent to functional equation for Riemann zeta. So maybe I should give a talk sometime on that. So is it my friend calling me? Okay. So, but anyhow, why we discuss this? Before I finish, if you give me 5 minutes, I want to go back to, remember we had an issue. What was the issue? The issue was that, so application to heat trace formulas. So this is application to number theory, but let me give you application to heat trace. Heat trace. Okay, so you remember heat trace was ZT equal to trace L2 of exponential of minus T. Well, okay, so we had a general positive, negative, self-adjoint elliptic operator. I look at this heat trace, but now I just look at Laplacian. And then this is some exponential of minus T down there, right? And from 1 to, it doesn't matter how you index it. Okay, so this is the heat trace, and these are eigenvalues of Laplace. So we applied this problem to the circle, this issue, I mean, this question to the circle. So as you know, for the circle, S1 over Z, the spectrum lambda, I mean, so we got something like this. We got that indeed lambda n is equal to 4 pi n squared, 4 pi squared n squared, right? 4 pi squared n squared. I mean, this has, I mean, it starts with 0 and so on. So 0 has multiplicity 1, but the other ones. So, okay, so what is that? That's equal to some exponential of minus 4 pi squared n squared t now, right? So n from 0 to infinity, but with multiplicity is counted, so here you should say n from minus infinity to infinity. So this operator trace, okay, is just theta function, our good old now theta function is theta of, well, what is it? 2 pi t, right? No, yeah, 4 pi t, sorry. Because remember theta t, what was theta t? Some exponential of minus pi n squared t, right? From 0, I'm sorry, and from minus infinity plus infinity, right? So this is really 4 pi t. Why 4 pi? 4 pi squared. No, 4 pi. 4 pi is okay. Okay, so, but remember we had an estimate. I said that, so this was the first thing, and then we said that at least for some classes of operators, we have this estimate near 0. That z of t is equal to 4 pi t to the power minus m over 2 times a0 plus a1t plus a2t, so on, right? That was the estimate that I didn't prove it. I said that this estimate exists in general, right? Okay, now if you look at this z of t in view of this is not obvious at all. This is not obvious because, well, this gives a very precise information as t goes to 0. It blows up like 1 over square root of, I mean, for n equal to 1, for example, for n equal to 1, the prediction is that, well, first of all, this is not equality. This is not an equality, sorry. This is asymptotic equivalence. 4 by t minus half a0 plus a1t. So so the question now is, what are a0, a1 for S1? Right? So we want to know what are these guys now, right? Again, from the formula, it's not clear at all what these guys are, because it's completely unwidely. I mean, this is just, yeah, we know that if this blows up by our first line of lecture today, you know, this blows up as 0, but this gives a very precise information how it blows up. It blows up to 1 over square root. And then there are these coefficients. So the question is, what are those coefficients? That's the question. And that's where actually this trace formula comes into rescue. So trace formula solves this problem. I mean, I don't see how to do this. Well, I know how to do it without trace formula also, but let me just do it using trace formula. That's it. Using trace formula, I mean, by trace formula, I really mean theta of t equal to 1 over root t, theta of 1 over t. We get, what do we get? Oh, first of all, what is z of t in terms of theta t? Again, I'm repeating myself. I derived it here. Z of t is equal to theta of 4 pi t, was it? 4 pi t. Okay, so now theta, so this is equal to 1 over square root of 4 pi t. Well, by this, right? 1 over square root of 4 pi t. And then theta of 1 over t. Now, notice that this is equal to, well, 1 over root 4 pi t. Now, what is this theta of 1 over t? As t goes to 0, this theta of 1 over t starts with 1, and then next term there is something like exponential of something, some coefficient times 1 over t, and so on. So as t goes to 0, these other terms are exponentially small. They are exponentially small. So this goes to 0. This goes to 0 fast. So you can completely neglect this part by this analysis. So asymptotically then, you're done. So this is asymptotic to 1 over square root of 4 pi t times 1 plus 0. So in other words, we just discovered that this term is equal to 1, this term is equal to 0. And this is thanks to functional equation, which is this Poisson summation formula. Right. So this is this, thanks to this functional equation. Right. So we have got that, right. Okay, so, right. Okay, so we are done. So what we did was that we had this okay, we had this trace formula, and then I indicated different applications of trace formula. So I think we should stop now. So let me stop the recording.